All right. Hi, everyone. All right. Now we are on part 6 of our exam 3, working on implementing the Crank-Nicolson method and plot the temperature profile as a function of time into our code. So what we have here is our code from part 3, and where we plotted our results from our expression from deriving the differencing scheme and calculating the time varying temperature profiles. And basically in part 3, we were showing the transition from stable to unstable results at a specific value of the discretization. And one way we showed that is if our delta t is at 0.5, which is our change in time segments, it is stable at 0.5, but if we change it by just one increment, you can see that it's unstable, and we showed that a little more depth in part 3 video. I'm just going to change this back real quick. And so what we're going to do in this is we're going to implement our Crank-Nicolson method, and we're going to stabilize that. So we're going to say from sci-fi lin alg. We're going to import solve banded, and then run that real quick so that's in there. And then the next thing is we're going to be using the conditions that we set in our first function. So we're going to go ahead and just copy those and bring them down here. The only thing that's changing in our initial conditions is our expression from the Crank-Nicolson method. We're going to divide that by 2 to average it out, and which will eventually stabilize our results. And then another thing we want to bring down is our array of our temperatures that we set in our indexing of the left-hand side and the right-hand side of our uniform bar for the temperatures, where we set T index 0 is the left side, and we set it to 50 degrees Celsius, and T negative 1 is the right side, in which we heated it to 80 degrees Celsius. And then to check our code, we're just going to run that real quick and check our array, see it's still looking good. Yep, still looks good. All right, so next step is, so we have a matrix for our expression, the left-hand side of our expression, that has 3 diagonals. And we want to put that in our code. So we're going to use NP zeros to do that. And I have my matrix over here. If you go to my past video, where is it? Yeah, if you go to part 5 and watch that video, you'll see the matrix. I'm not really sure how to share the matrix with my code, so I'm just going to walk you through it. So for our function, we're going to have the shape as our nodes, spatial nodes. Oh wait, our shape. So we have 3 diagonals, which is the shape of our matrix, and then our array, our parameter is going to be our spatial divisions, our nodes of the bar, minus 2, and then we want to specify each diagonal. So for A matrix, or A index 0, 1, colon, this is going to represent our first matrix, not our first matrix, so we have our matrix. We have 3 diagonals that we're implementing here. And so indexing 0, 1 will show our first, will represent our first diagonal, which is, let's see, 1 plus 2. And then we're going to index 1, colon, comma, colon, for our second diagonal, which is going to be negative r. So we have our top diagonal, our middle diagonal, which is what we're putting in here, and then for our bottom half, we're going to do 2, colon, negative 1 for numpy indexing. And that is going out, so this is actually negative r. And this is actually, excuse me, 1 plus 2 times r. Okay, and so now that we have our matrix of, now that we have set our matrix with our top, middle, and lower diagonals, we can, run our code. Actually, hold on. Cannot interpret 48 as a data type. What does that mean? Maybe if I found that sometimes if you just add it into different code. No, it's still a problem. Excuse me. Okay, I was just missing some parentheses. Errors I've had in the past, I found that if you just retype it into a new code or new text, it'll work a little smoother. So what we're going to do here, now that we have our matrix, we're just going to run that and then check it. Should go if you just do a. Okay, so this looks good. So this shows our top diagonal, our middle diagonal, and our lower diagonal. The values look about that. Excuse me, my cat is running around. Okay, so now that we have our matrix in order, we want to start defining the right-hand side as a vector for our problem. So we say numpy zeros again, And this time we just gonna say our spatial divisions minus 2 again. And then put in our expression, which is going to be the R expression times T index 2 plus T index 2 plus 1. Okay, 1 minus 2 times R plus RT 1 to negative 1 plus R times. Okay, so now that we have our expression in there, let's just check that this looks good. No, I don't think these parentheses should be there. Well, let's just finish it, and then we'll see if there's still an error when we're done. Alright, so that looks good. So now we're going to start by defining our first element of our right-hand side vector. And we're going to index that as 0 equals, let's get our equation here. Equals would be our first element plus our expression times T index at 0. And then for our last element, we're going to index that as negative 1. So the right-hand side expression is going to be negative 1 plus same, but our expression times the temperature for our last element. That should be negative 1. Alright, now that we've defined those, let's see if it's still saying there's an error. And there is, so really sure what its issue is here. Let me look at my notes from lecture of my work, not of our expression. So it's our expression times our second temperature, so T2, plus 1 minus 2 times the R expression, plus R times our last temperature value. Yeah, that should be right. So it's just saying invalid syntax. Oh, okay. Ooh, forgot a T. Okay. And so what we're going to do to check our code is we are going to create an array. So we're going to do np or x equals np nb arrange and set those parameters to, let's say, from 1 to 5 or 1 to 4. Oh. Or from 0 to 4. So we get 5 values. So this is just showing that. So we defined our x up here as a range of numbers, so we can pick. We can pull from our 50 set of increments here, and basically this array allows us to choose those segments and solve for them. So this is just showing us, we're checking that it is pulling from that range and that we can move forward knowing that we can put in our expressions. Now we are going to make another graph with our new expression, and we're going to call that figure 2. Let's make subplots. I'm going to give it one row and one column. And then we're going to say fig 2 add scatter with our x axis is going to be the nodes, and our y-axis is going to be our initial temperatures. And we're just going to call it initial again. And then we're going to graph that. Ew. So, yeah, I'm going to redo this video anyway, so it's fine. So what went wrong here is, maybe I need to run all of it. Okay, yeah. All right, so we just had to run the whole code because it was just running this. And so since I separated this from our initial conditions, it didn't account for our array of temperatures where we heated the left side at 50 degrees Celsius and the right side at 80 degrees Celsius. But now that we have graphed that, we can see that it looks good. And now we can go ahead and add our next function. All right, so for our next function, we're going to solve for the next temperature, for the next increment in time. And so what we want to do for that is we want to create a range that is going to count each increment. So as it solves, it'll solve for the next temperature and the next temperature. So for I in range, we're going to use our time steps plus 1 to count. And then we're just going to define our index from, this is not working, 1 to the other side of our bar. So counting all what is it? All of our increments in our uniform bar. And then we're going to say use the solve banded function to solve for that using our matrix that we included. Yeah, so this is going to solve for our series of equations or series of functions, algebraic equations. Okay, so 1A, and then our matrix, and then our vector. So this is our left-hand side, which is of the expression, which is our matrix, and the right-hand side, which is our vector of linear equations. We have the right number of parentheses, so it looks good. And then we are just going to reiterate our expression here, down here in our for loop. So I'm going to copy and paste that. Okay, and I believe next, that is all the expressions we need to add. So let's try graphing it and see if it's calculating right. So I guess we can just copy and paste this as well here. Okay. And I forgot my one. For I in range, we need a colon. I don't think I need to add a parenthesis, but it says an indentation error. Okay. So I'm just going to well, actually, before we think of there being indentation errors, let's run the whole code real quick. Alright, so there's definitely something in this function that's not working. That is very unstable. I think the issue is, okay. No, I don't think that doesn't matter. So, need a second to think what's going on here. Well, for our first problem, our issue is it's only calculating 2 initial temperatures. And we need to calculate 50 or 48. So let's just try some indexing. Maybe this is our issue. It needs to be in the for loop. I think I'm missing my if then statement. So if our increments is, yeah, because we have a large number here. So if we divide that by 0 or 100, maybe it's just taking it too much. And now I'm getting nothing. And that's not. Oh. Big. 2. Okay, so it's still not calculating. I think I have a negative somewhere. Let's also try using decimals, because if you don't put the decimals, then it just rounds it up to an integer, and this can also create errors in your graphs or in your code. So let's just see. Say 2.0. That should be all of them. Yeah. Let's just try it. And that's not the issue either. I'm not sure why, because we have all of our expressions, and it worked up here for, okay, so maybe that's what we need to do. So it worked up here for our first part of the code. Now what are we missing? We have that expression. So for I in range, I don't think we need to add this to that box. Get rid of that real quick. What's the issue with my T? What's the error? Value error. In T plus 1. Array must not contain NFS in NANS. All float, do not, and not NP is finite AL numbers. Well, okay. So let's just try. Sometimes retyping it will also do the trick. That did not do the trick.